Firstly, let's examine the material for this groundwater vulnerability study. It is a packaged project file. All the content required for this study is condensed in this PPF file, which is compatible with Esri's ArcGIS Pro, the world's leading location analytics and mapping software. Because it is a project file, the contents are loaded onto the map view of the software directly. The MC boundary layer stands for Morrow County boundary. Morrow County is our area of interest for this study. This county is located in the state of Oregon in USA. Besides this layer, there are two other layers which are part of the project file. It is the soil layer and the land cover layer for this area of interest. Let's change the base map to satellite imagery. The imagery view allows us to get an aerial perspective of our area of interest. Its dark shade also serves as a contrast to the bright colors of the layer files. Let's examine the soil layer. One cannot discern much from this layer, visually at least, but this layer is very important for us in terms of the data it contains. So let's examine it by opening the attribute table. There are 8000 plus polygons in this layer file. As you can understand, because we are doing a groundwater vulnerability study, the contaminants seep into the soil and into the groundwater. So hence, therefore, this layer is very important. Within this layer, there are two particular columns of importance. One is the drainage class and the water table depth. To get a macro level understanding of the data points, we can also examine the summary statistics. So let's do the same for the drainage class field. This field comprises of 5 categories, ranging from excessively drained soil to poorly drained soil. In Morrow County, the maximum occurrences is of well-drained soil with nearly 8000 polygons dedicated to it. To understand the importance of this field, the drainage will indicate to us how readily will the contaminants flow into the water table. Next, let's examine the summary statistics of the water table depth. It ranges from 0 to 92 centimeters with an average of 70 centimeters. The higher the water table depth, the less probability for the contaminant to reach the groundwater. Let's examine the second important data set for our study, which is the land cover. As you can see, it is a multicolored visualization. Our area of interest contains several land cover classes, ranging from open water to developed spaces, barren land, forests, agricultural lands, and wetlands. From a groundwater vulnerability perspective, you should know that agricultural lands and developed lands contribute to the maximum groundwater pollution because the contaminants are mostly generated from agricultural fields in the form of fertilizers, pesticides, and so on, and also from developed lands in the form of the hazardous material or the leakages from septic tanks and so on. What we are doing next is adjusting the map-based projection. Selecting the right coordinate system as per the nature of the study as well as the dynamics of the area of interest would allow us to perform the geospatial analysis subsequently in an accurate manner. We will change the coordinate system to a US-centric coordinate system, in particular for the Oregon state. Projected coordinate system and map-based projection are technical topics, but very interesting nonetheless, and I would recommend you to search for it online in case you are interested to know more. Notice how the visual has changed from before. Let me toggle the views. This is the before view and this is the after view. It has become noticeably thinner. What we will do next is to make this setting for all our analysis outputs, so that all our geospatial analysis which we will do subsequently will carry the similar projection. So one objective which is fulfilled is that all the layer output will be comparable. Once we've made this change in the environment field, we are now ready to prepare the final stage of the data, which is the conversion of polygon to raster. As you are aware, the soil layer and the land cover layer were both polygon layers, as in comprising of multiple shapes of various sizes. What this step will do is to convert both these layers in a raster format. In a raster format, each pixel will carry a unique value instead of the entire shape. What this will do is to again make the input layers standardized and comparable, which would help us in a subsequent step when we identify zones which are most prone and vulnerable to groundwater contamination. Using the polygon to raster geoprocessing tool, firstly we've created a raster layer out of the drainage class field within the soils layer. In the map view, you can see the color is as per the 5 categories of the drainage classes, ranging from poorly drained to excessively drained soil. Subsequently, we'll use the same geoprocessing tool to visualize the water table depth in a separate raster format. Initially, if you remember, we were just visualizing the soil layer as per the polygons. Now, the interpretation on the map view is much more easier. The water table depth raster has been prepared, and once again, the color combinations are as per the depth of the groundwater table. In Morrow County, you can see that brown and light pink colors, which are 74 and 89 centimeters of water depth, are prevalent, the maximum, whereas the northern portion has a 0 centimeter of water depth. Now that we have prepared our datasets, we can proceed to the analysis phase. Suitability Modeler is a very powerful feature within ArcGIS Pro, which would allow us to perform location analytics and identify sites which are prone to groundwater contamination. We'll name the model name as vulnerability analysis and the input type as criteria. The scores will range from 1 to 5 and the weightage will be on a multiplier basis. We will name the output raster as vulnerability analysis and proceed to save this model. In this model, we will now assign weightage to the criteria variables and iterate the sites. In our first iteration to determine groundwater vulnerable areas, we will make use of 2 layers out of the 3 available to us. The first one being soil drainage conditions and the other one being the water table depth. By default, a weightage of 1 has been automatically assigned by the model. Let's close the open layers to have a clean map view. Our next step involves data transformation. Doing this step well and understanding the technicalities behind it will lead to better analysis and overall a better project outcome. So let's first begin by transforming the soil drainage conditions layer. The transformed layer has been added underneath the suitability model grouping. There is also a summary layer known as vulnerability areas, which we temporarily do not need, and so we will switch it off. We will also temporarily switch off the auto calculate function. Data transformation entails studying the existing distribution of the data within the selected layer. To aid us, there is a chart on the left of the transformation pane. Knowing what the objective of transformation is key to doing this step effectively. By default, the suitability model assigns random scores to the data fields in the layer. Our objective is to firstly modify the method of transformation using the central section of the transformation pane. Subsequently, we will also assign meaningful suitability scores to the data fields. The structure of the data post-transformation can be visualized from the histogram on the right, which depicts the data clusters from a low suitability score of 1 to a high suitability score of 5. Because the soil drainage layer consists of 5 distinct types of soil, each of which can be uniquely scored, we will therefore select the unique categories type of data transformation. By default, each of the soil drainage types has been assigned a unique score from 1 to 5 randomly by the suitability model, which begs the question, what is our objective? High groundwater vulnerable areas are the ones with high soil drainage potential and vice versa. Hence, we will assign the scores accordingly. For excessively drained type of soil, we will assign the highest suitability score of 5, while on the other extreme, poorly drained soil is the least vulnerable to groundwater pollution, and hence we will assign a suitability score of 1. All the fields will be assigned a unique suitability score. From the histogram on the right, you can see that the well-drained soil is the most recurring pixel, and in the transform layer, it will be assigned a yellow color, which indicates medium risk of groundwater pollution. To visualize the transform layer, we will now click the calculate button. The map view updates with the transformation of this particular soil drainage layer. Areas which are highly susceptible to groundwater pollution based on the soil drainage type have been color coded in shades of green, whereas areas which are least susceptible to water pollution has been color coded in shades of red. This may appear slightly counterintuitive, but know that we had given high suitability scores to highly vulnerable areas. With this step, we have completed the transformation of the soil drainage layer and can proceed to transform the water table depth layer. Firstly, we will understand how the data within this layer is structured. Water table depth contains several depth values all the way up to 92 centimeters, and to use the unique categories method of transformation would entail assigning scores to all distinct depth values, which is not very practical in nature. This problem can be solved by using the range of classes method of data transformation. As the name indicates, the depth values are classified into distinct class ranges. Again, how these classes are structured needs to be decided based on the distribution of the depth data points. You already know that this layer does not have proportionately distributed data points. Maximum values of depth range from between 60 to 90 centimeters only. Hence, to use the equal interval method is not the most practical option. The natural Jenks method, in contrast, splits the water table depth dataset into much more meaningful classes, an aspect which is possible because it minimizes the variance of the class values within a group from the class mean. Once we apply it, you can notice that the class ranges are not proportional in nature. It begins from 0 to 10, increases to 10 to 33, reduces to 33 to 61, and so on. But the distribution of the data points within each classes is much more proportional in nature. Notice one anomaly. A low suitability score is assigned to low water table depth values, which is not what we want, hence we will reverse it. This is because the chances of groundwater contamination are high if the water table depth is low. Once we have done this, it is time to calculate the suitability model for this particular layer. Let me close the transformation pane to bring the map into full view. Don't be alarmed by the burst of red in the area of interest. As I had reminded you in the soil drainage layer as well, it is the green color which indicates the high suitability score, which in turn indicates the higher risk of groundwater contamination. So, the bottom left of the area of interest has the highest chances of groundwater vulnerability based on the water table depth layer. Let me just open the soil drainage layer to show you a contrast. In the soil drainage layer, the most vulnerable areas were lying to the north of the area of interest, just adjacent to the river. Whereas in the water table depth layer, the most vulnerable areas are located to the south of the area of interest. So how will this contrast reflect in the combined suitability model output? Let's open the vulnerability areas layer to see this result. As you will mentally process this map view, you will realize that the northern section of the area of interest, which was colored in dark green in the soil drainage transformation, has now lightened in shade considerably because of the impact of the low suitability score from the water table depth transformation. In the legend, you will see that the pixel values range from a minimum of 3 to a maximum of 8. Remember that both the layer values were scored between 1 and 5 in their individual transformation, and because these layers themselves carry a weightage of 1 each in the suitability model, the overall score assigned is just by mere addition. 1 into 5 plus 1 into 3 will be the result of a particular pixel if the values are 5 and 3 respectively in both the layers. Be aware that the true max and minimum for this dataset can be 10 and 2 respectively, but because of the inherent dichotomy in the nature of the result of the two layer transformations, no pixel values carry these extreme scores. We will now proceed to change the weightage assigned to both these layers from the default of 1. We do so out of practical necessity because in our groundwater vulnerability study, the soil drainage condition is a slightly more important parameter. So, a ratio of 5:4 for these two parameters will do justice to the outcome of the study. Once we hit calculate, the map view updates with the revised scores. And you can see on the legend on the left that pixel values now range from the minimum of 14 to a maximum of 37. Clicking on the Run button in the Suitability Modeler pane allows us to save our model output. We are doing so because our first iteration is complete now. To recollect, we had used the soil drainage and the water table depth layers as inputs, proceeded to transform the dataset with meaningful suitability scores, assigned proportionate weightages to the two layers overall, and the software used the weighted average multiplication to arrive at the combined suitability model output. Be aware that the scores could have potentially ranged from a minimum of 9 to a maximum of 45, but because of the contrasting individual layer scores, the overall pixel values do not carry these extremes. As is evident, one can click the map view to inspect the pixel values at our desired spots. Next up, we will include the land cover layer as well in our groundwater vulnerability analysis via the Suitability Modeler route in ArcGIS Pro. Let's expand the land cover layer first. As you would recollect, there are a variety of land cover classes within the layer. Among these, if you were to think of it, the developed land cover class and the cultivated crops land cover class, which is in essence the agriculture or farmland land cover class, would contribute the most to groundwater contamination. This is so because in farmlands, the use of pollutants such as fertilizers and pesticides would contaminate the groundwater table, whereas in urban areas, industrial activity would often lead to the release of chemicals into the water system, thereby polluting it. We will keep this aspect in mind when we transform the land cover dataset in the next iteration of the suitability model. Let us organize the various layers in the content pane before proceeding to create a new suitability model. We will name our new suitability model as groundwater risk zones. This time, instead of a maximum suitability score of 5, we will set a larger cap of 10 because we would be dealing with a larger number of criterion values and classes. Let's name the output suitability raster as risk zones and proceed to save this model. As our input variables, we will add the land cover layer as well as the output of the previous iteration of the suitability model. In essence, we are using all the three information layers available with us as our input variables in this iteration of the suitability model. This time around, we will assign the weightages in advance. The land cover class will carry a weightage of 10, whereas the previous suitability output, which was by itself a weighted average combination of soil drainage and water table depth, will be assigned a score of 8. Hence, the land cover class is placed a larger relative importance than the previous two layers. We will first begin by transforming the vulnerability analysis suitability model output from the previous iteration. The vulnerability areas dataset does not contain any category or class-based information. It just contains pixel values from our previous suitability modeler iteration. Hence, the continuous functions method of transformation would be appropriate in this scenario. There are several functions for us to try. The key to selecting the right function is to see whether the output of that function, as depicted in the histogram on the right, is how we would like our dataset to be transformed or not. For example, if we apply the Gaussian function, the tails of the dataset's values are assigned low scores, whereas the bell is assigned high scores. If we were to apply the exponential function, the smaller pixel values of our dataset would be assigned low scores, but as the pixel values increase, there would be a disproportionate and an even larger increase in the scores assigned to it. The key over here is to see the shape of the curve on the histogram, which will give us a lot of clues. Let's try the ms_large function. In this function, the very large pixel values in our dataset are assigned higher suitability scores, which is not right for our intended, outcome which we are targeting. As we change the function, the map view also updates, and that could also be useful in our analysis. This happens because we have selected the auto-calculate function above. Let's try the linear function. What we see over here in the shape of the curve, that there is a very progressive and systematic increase in the pixel values. Now, this seems to be the right approach because we want the low vulnerability areas to be given a low score, and as there is an increase in the vulnerability, we want a higher score assigned to it. So, we shall use this particular method of transforming the dataset. Once we have decided which method is appropriate, we can, move on to the next layer which we want to transform, which in our case is the land cover layer. The unique categories method of transformation would be appropriate for this scenario, as there are very distinct classes of land covers in our dataset. The suitability modeler randomly assigns a score between 1 to 10 to each of the land cover classes. Our job is to assign an appropriate score based on the land cover classes' individual propensity to contaminate the groundwater. As I have already explained earlier in this video, the developed spaces and the agricultural farmlands pollute the groundwater the most, and hence we shall assign very high scores to these two types of land covers in particular. I have a predetermined list of scores for each of the land covers, so let me quickly insert it. Barren land, forests, scrubs, hay, open water bodies are all types of land cover which are not contaminating the groundwater that much, so we will assign low scores to it. However, the developed spaces, as you can already see, there are 4 subclasses. We have assigned high scores to it. And also we have assigned high score to cultivated crop, which essentially is the agricultural farmland. Let's calculate the suitability model. The land cover layer has been transformed based on our updated suitability scores. The dark green areas signify the presence of those land covers which pose the maximum threat to groundwater, that is the farmlands and developed spaces respectively. We can inspect the scores by clicking on the map view at the desired location. Now that we have transformed both the parameter layers, that is the vulnerability analysis and the land covers, we can see the combined site suitability model output now. The dark green areas lie on the northernmost section of the area of interest adjacent to the river. These areas pose the highest risk to groundwater contamination after factoring in all the 3 parameters critical in our study, namely the soil drainage conditions layer, water table depth layer, and the land cover layer respectively. The pixel values in our suitability model ranges from a minimum of 80 to a maximum of 168. We can inspect these scores at our particular spots of interest by clicking on the map view as well. Let's observe the output closely now. We can use bookmarked views to hover around the areas which we have determined to be critical for us. So for example, the 6 green circles present in this map view. We will use the swipe tool, which will allow us to toggle between the imagery view and the output view. What we can notice is that these appear to be high intensity developed spaces, most likely to be a sewage treatment plant. Let's go to another bookmarked view, which contains dark green spots. By using the swipe tool, we can see that these appear to be something very similar to a port operation. So Morrow County, our area of interest, contains a river port besides the river. So this is likely to be port activity. Let's zoom out. We will save the output because our iteration 2 of this model is now complete. As part of our third and final iteration, our objective is to identify those areas within the high risk zones identified as part of the second iteration, which can be targeted or earmarked for conservation efforts. To assist us in this objective, we will use the CON tool, which is short for conditional evaluation. The input dataset for this tool will be the suitability model generated in our previous iteration. What we are asking CON geoprocessing tool to do is to extract only those pixels from the input layer which are greater than 100 in value. Essentially, these are the dark green pixels which you are seeing on your map view, which carry the most threat to groundwater contamination as well. This is the first phase of our analysis. We will use the CON tool once again to identify those areas within these greater than 100 high risk zones which can be earmarked for conservation efforts. Upon running the CON tool, we can see that the desired conditional layer comprising the greater than 100 valued pixels or the dark green pixels has been extracted. This new layer is color coded from black to white, black denoting those pixel values which are nearer to the lower limit of 100, while whiter shades denote those pixel values closer to the upper limit of 167. We can randomly inspect the scores manually by clicking on the map view to see if these are greater than 100 in value. So now, which areas from within this newly generated layer would you earmark for protection and conservation efforts? If you were to think about it carefully, we cannot target those patches of land which are already being intensively used, either for industrial purposes, farming purposes, residential purposes, and so on. However, we can certainly look to protect those areas which are currently undeveloped. Example, forests, barren lands, grasslands, wetlands, and so on. In the second run of the CON tool, we'll ask the tool to conditionally evaluate and extract exactly these type of land cover classes from the land cover dataset. We will select these land cover classes from the list. We will name the output layer as undeveloped areas. Can we run the CON tool now? Not really, because if we were to run it in this way, the tool will extract the land cover classes from the entire area of interest. This is not what we want. We want the land cover classes to be extracted from the pixel values which are greater than 100, which is the output of our previous CON tool. Therefore, we will insert high risk zones, which was the new black and white layer which was generated, as our mask in the environment section. Now we are ready to run the CON tool. Hang on, there doesn't seem to be any output in the map view. Have we made a mistake? Not really. Just that the extracted zones are very small in nature. So we will zoom into the area near the river. These red spots are the spots which can be targeted for the conservation effort. These are not the only spots in the map view. There are several such clusters. In the attribute table of this newly generated layer, you can see that there are 3 distinct types of land cover classes which have been extracted. It is currently named as 31, 52 and 81, which is the serial number, but we will soon identify which are those 3 land covers which have been identified. So number 31 stands for barren land, 52 stands for shrub or scrub land, and 81 stands for the hay or pasture land. Let's change the legend from the symbology pane to make it much more meaningful for viewers. We will name the legend as land cover classes and give the respective names which we had identified from the attribute table. As we make the edit over here, you can see on the left on your content pane that the legend has been modified also in parallel. From the attribute table, you can see that the hay or pasture land has the maximum number of extracted pixels, which is 615 of them, followed by barren land, which has 63 pixels, and lastly shrub and scrub land, which has only 5 pixels from the entire area of interest. Hence, the number of pixels are very small, and which is why we need to zoom into the map view to spot where these are located. But once these are located, we can toggle them on the imagery base map to see whether the pixels are correctly identified and whether those land cover are what they are presumed to be. Sometimes when the pixels are very tiny, we can also change the color of the pixel so as to make it much more contrasting on the imagery base map. So once we have selected the pixel type 31, which is the barren land, it gets automatically highlighted in the map view. So once we remove our selection, you can see that these are the yellow pixels or the barren land pixels. So while we can continue our treasure hunt to identify these tiny clusters which are to be prioritized for protection and conservation efforts, as they are undeveloped, I think you've understood and appreciated the method involved in doing so, which is suitability modeling. Besides the powerful analytics which GIS softwares such as this one, ArcGIS Pro, is capable to perform, you would also need authoritative and updated Geodatasets to perform similar workflows in your preferred area of interest. To summarize, in this workflow, we've used 3 iterations of suitability modeling to identify highly groundwater vulnerable areas. First with soil drainage and water depth layers, and subsequently we've also included the land cover layer. Lastly, we conditionally evaluated the risky zones to identify undeveloped areas which can be prioritized for conservation activities. Thank you for watching.